Now we are going to start with Unit 3 that talks about aspects of light. Aspects of light. And the first chapter of this unit is chapter 13 in your book. Chapter 13 that talks about electromagnetic waves and diffraction of light. So that chapter consists of two parts, electromagnetic waves and diffraction of light. So I am going to deal with each part alone. I am going to start with electromagnetic waves. Okay? Electromagnetic waves. In the first secondary and second secondary, you studied, in addition to electromagnetic waves, you studied mechanical waves. Mechanical waves, what are they? They are waves that need a medium to propagate through, like sound waves, waves in ropes, waves in water. All these waves are examples about mechanical waves. But in this chapter, we are interested only with electromagnetic waves. Because of this, we are going to study them well. I am going to define them and give their characteristics. Okay, let's start with the definition. Electromagnetic waves are oscillating electric and magnetic fields. Okay, what does this mean? Let's see the figure here. Look at it. You notice here that there are electric field, there are electric field and magnetic field oscillating, as you see. They are perpendicular to each other and perpendicular to the direction of propagation. This is the direction of propagation of the wave, okay, parallel to the x-axis. As you see here, they oscillate sinusoidally. So, they oscillate sinusoidally and they are in phase. Notice here, they reach maximum at the same time. This is maximum, this is maximum. They reach zero at the same time. So, since they oscillate sinusoidally, what is the expression of each one? Okay? So, A has the expression of sinusoidal waves, E equal Em sine omega t, will B have the same Bm sine omega t. They are in phase. Notice here that the phase difference between them is zero. If I find the phase difference, I get zero. Okay, because they are in phase, they reach maximum, minimum, and zero at the same time. So these are the expressions of A and B. Also, in addition, we said that E perpendicular to B and perpendicular to the direction of propagation of the wave, okay? Right. This was the definition. Now, waves have characteristics. What are the characteristics of the electromagnetic waves? The characteristics. Let's see. Let's look at this image. This image shows the direction of propagation of the wave. The blue one is the electric field, which is perpendicular to the field. This is the magnetic field. Look here. This maximum value of the electric field is the amplitude of the electric field. And the maximum value of the magnetic field is the amplitude of the magnetic field. So the first characteristic I am going to write is the amplitude. So an electromagnetic wave has two amplitudes. Amplitude of the electric field and amplitude of the magnetic field. Okay? Two, it has period. It has period T and the frequency F. Okay? Like all waves, as you know. And the relation between them is T equal 1 over F. This is in hertz and T is in second. But from now on, we are going to change the notation of the frequency from F to a Greek letter called nu. Yani, this implies I'm going to change the notation of F from now on so that T is equal 1 over nu. So from now on, when you see nu, it represents the frequency of the wave. 3, it has a speed V. Okay? V, it has a speed because it moves from one place to another. And as you know, the speed of the wave is equal x over t. Okay, where x is the distance covered by the wave during time t. The SI unit of the speed is, this is meter, this is second, you get this one meter per second. Okay, this is SI unit, but sometimes we use the centimeter. Okay, x, if x is in centimeter, t in second, you get V centimeter per second. Okay, but this is not an SI unit because centimeter is not an SI unit. Now, as you know, the speed of the wave depends on the characteristics of the medium and not on the period and not on the frequency and not on the amplitude. So V depends on the characteristics of the medium. What does this mean? As you know, light is one of the electromagnetic waves. Light, in reality, is an electromagnetic wave. Its speed in vacuum is a 3 times 10 power 8. If light passes to glass or to water, its speed will change because the medium has totally changed. Although, if I change its frequency or its period, the fourth property is wavelength. Wavelength, okay? Represented by lambda. Also, you know that the wavelength is the distance covered by the wave during one period. فإذن it is the distance covered by the wave during one period. Okay? If you look at this formula, cross multiply, you get x equal Vt from this formula. Here, x is the distance covered during any time t. Now, if I take a specific time, which is period, then the distance covered will be lambda. So substitute, you get lambda equal Vt. In SI system, this is in second, meter per second, this is meter. SI system, but sometimes we use centimeter. This is centimeter per second, this is second. Now, replace t by 1 over the frequency nu here. You get lambda equal V over nu. Also, this is meter per second, hertz, this is meter. Here in SI system, sometimes we use centimeter per second, hertz. You get this in centimeter, okay? Right. If we look at the figure, what is lambda? This is lambda. It is between two crests, okay? It is the distance between two crests, here or here, between two crests, or the distance between two troughs, okay? Or the distance from one point to another point where the wave repeats itself. This is lambda, okay? The fourth properties, we have finished it. Every electromagnetic wave has these four properties, and all of them have the following properties. They can propagate in vacuum, okay? In vacuum. Also, in vacuum, all of them in vacuum have a speed. They have speed c approximately equal 3 times 10 power 8 meter per second. And all of them, they are transverse. They are transverse. What do you mean by transverse? I mean by transverse that E or B are always perpendicular to the direction of propagation. All the times, A and B cannot be parallel to the direction of propagation. Okay. What are the electromagnetic waves that exist in nature? You should know them. They form the electromagnetic waves that exist in nature, form what's called electromagnetic spectrum. Electromagnetic spectrum. What do you mean by word spectrum and the two words electromagnetic spectrum? Let's look at this image. Look at this image. All the radiations from here to here, you have infinite of radiations. All these radiations starting from the minimum lambda of gamma rays to the maximum lambda or wavelengths of radio waves, all these radiations consist what's called electromagnetic spectrum. Yeah, it is the set of all electromagnetic radiations, okay, where each radiation has different lambda and the frequency from the other one. Let's look at them. First, you have gamma rays. These electromagnetic waves are arranged in increasing lambda, as you see. The first gamma ray here has minimum wavelengths, and the last radio wave here has maximum wavelengths. Let's look at them. If you notice, or if you look at the figure well, you notice that each kind of electromagnetic waves have certain range. يعني مثلا for example الgamma rays have minimum wavelengths and maximum wavelengths. All the electromagnetic radiations that are gamma rays lie between this range, and they are infinite. Similarly, X-rays, as you see, they have range, okay? Minimum value to maximum value. Then you have the ultraviolet, الأشعة فوق البنفسجية, as you know. Then you have the visible light. This is the visible light. Then you have the infrared. Also, it has range. Then you have the microwaves, and finally you have the radio waves. To enjoy this, let's talk about their origin or their uses. The gamma rays, the sun gives gamma rays, okay? Also, radioactive material like uranium, radium, found in nature, they emit gamma rays, and gamma rays are very dangerous. They have high penetrating power, and we are going to study them well in radioactivity. Now, X-rays, all of us heard about X-rays. The photographs done for the bones or for the teeth are done by X-rays, okay? Ultraviolet. الالترافايولت اللي هي الاشعه فوق البنفسجيه also it is dangerous. It causes cancer for the skin if we are exposed a lot in it. So it is very dangerous. And I like to say that the ozone layer in the upper atmosphere has the role to absorb a lot of dangerous ultraviolet radiation. After the ultraviolet radiation, you have visible light. The visible light, all of us know the visible light, and it is the most important electromagnetic wave because it causes the sensation of the vision. Then you have the infrared. الانفراريد يعني الأشعة تحت الحمراء. الانفراريد, it is responsible about the warmth of our bodies and the warmth of the earth, and every body at room temperature emit and absorbs infrared radiation. Okay? Some uses of the infrared radiation is the remote control at your home for TVs and other devices. The infrared used also in missiles. Okay? SAM 7 كانوا يستعملوه لحتى ينزلوا الطيارات. كيف كانوا ينزلوا الطيارات؟ كيف مبدأه أنه SAM 7 بيلحق الانفراريد راديشن، والانجن بيكون اسخن، بيطلع انفراريد راديشن اكثر من جسم الطياره، فكان هن يصنعوه على اساس يلحق الانفراريد تاعت الانجن. بعدين البوالين الحراريه ليش بيستعملوها؟ البوالين الحراريه تعطي انفراريد راديشن اكثر من الانجن، فبدل ما يلحق الانجن بيلحق البالون الحراري فبتزمط الطياره. اوكي، المايكروويفز all of us hear about microwave. المايكروويف oven, one of the uses of microwave, and all of us know it, is the microwave oven. Okay, and finally you have the radio waves that are used in TV, television and radio communications. Okay? فإذن they are classified in increasing lambda. هيدي increasing lambda, you have first gamma rays, then you have X-rays, then you have ultraviolet, then you have light, then you have infrared, microwaves, and finally radio waves. If these are classified in increasing lambda, the reverse is for the wavelengths. Okay? The reverse is for the frequency. This is the frequency. يعني I mean here, the radio waves that have maximum lambda, they have the minimum frequency. Okay? Why? Because the frequency is equal lambda V over lambda. Okay? So, as lambda decreases, the frequency increases, and in vacuum, V equals C. We write also C over lambda, and as you see, lambda decreases, the frequency increases. Now, what is important? What is the most important electromagnetic wave? We said light is the most important. Because of this, I am going to talk about light. Light. How we define light? Light is an electromagnetic wave that causes the sensation of the vision. It is an electromagnetic wave that causes the sensation of vision. Okay? All the radiation that consists the light, whose range is between 400 nanometer and 800 nanometer, form the light that we see. Okay? And from 400 to 800, you have infinite of light radiations. And not only 7 radiations or 7 colors, as you know, or as you say. Okay, these 7 colors, they are infinite of radiation. Why? Because red, you have dark red, then less dark, less dark, less dark, till we reach the brighter light or the lighter light, then we enter the orange region. So between the most dark red and the lighter dark, you have infinite of red radiations. Okay, similarly for the orange, then yellow, then green, then blue, then violet. Okay, between them there are yellow-green and blue-green. Light, you have 2 types of light. You have monochromatic light. Okay, you have monochromatic light. You have monochromatic light, and you have also polychromatic light. What is the difference between this? The monochromatic light is the light that has one radiation, yani consists only of one radiation that has specific value of lambda or a specific value of the frequency. فإذن, it is a radiation with specific lambda or frequency. For example, about this, if the laser light, let's see why laser is monochromatic light. Look here. Look at this figure here. This is a prism, and here this is a laser light. It has one color, only one color. It is one radiation. It undergoes refraction at one side, then continues and undergoes refraction at the other side, and emerges from the prism with same color, يعني with same frequency. يعني it enters with frequency mu and leaves with the frequency mu without changing its frequency. This means that it is only one color. يعني one radiation. So laser light is monochromatic light. Here, this is a schematic drawing. We send here a laser beam. It makes double refraction here, and then it leaves as one radiation. This is an analogy to this real situation. Okay, so laser light is monochromatic light. Now, polychromatic light is a light consists of many radiation. Polychromatic light, here it is a radiation. Polychromatic light, it is light that consists of many radiations. Okay. Example is the white light. White light is an example about polychromatic light, and it is the most important light here because all the light around us coming from the sun is called to be white light. So I am going to talk about white light. Okay. فإذن الوايت لايت the sun gives white light. Also, the incandescent lamp in your homes emit white light. الانكاندسنت لامب هي اللمبة الصفراء اللي إلها فيلامنت بنسميها incandescent lamp. يعني sun and incandescent lamp أو bulb emit white light. Incandescent lamp is like this. It is the lamp at your home that gives a yellow light. You see it as yellow light, but it is what? It is white light. هيدا. This is called white light. طيب. If you look at the light of the sun, which is white light, or the light given by incandescent lamp, you will say that it is one color, which around yellow, like this. But in reality, it is not one color. So, how can I know whether the light is monochromatic or polychromatic? Let's see here. I am going to repeat the same experiment here, but instead of inciding a laser light to the prism, I am going to send a white light toward the prism. Let's see, what do we observe if we do this? Look here, look at this image. This is the prism, and here this is the white light. When you look at this side, this is called incident beam, you will say that it is one color. But in reality, if I let it pass through the prism, this one color will be divided into infinite of components. Infinite of components, from dark red to the lighter violet. The schematic drawing of this is this one. This is the white light. It makes double refraction at one side, then refraction at the other side. And here all the radiations are collected on a screen. And you see these radiations are divided into 7 categories: red, orange, yellow, green, blue, indigo, and violet. And each category has its own range of wavelengths. Look here, this is a range of wavelengths. You have from here to here infinite of radiation. Similarly for the orange, for yellow, for green, for blue, for indigo, for violet. So I can put a definition for the white light. Okay. The white light is a polychromatic light that consists of radiations that have lambdas lie in the range lambda between 0.4 micrometer to 0.8 micrometer. Also, this range, I can write it in this form: 0.4 micrometer, 0.8 micrometer in vacuum. When you write the range of lambda, you should mention the medium. Why? Because lambda depends on the medium. Because lambda depends on the medium. Okay? Type 0.4. What does 0.4 represent? 0.4 represents the lighter violet, يعني this one here. Okay? هيدي 0.4 micrometer. فإذا هيدي بسميها extreme violet. يعني هون المقصود الحد المينيموم ليميت. هلا below 0.4 you have ultraviolet. The range of ultraviolet is from 0.4 micrometer till 6 times 10 power minus 4 micrometer. All the radiation within this range are ultraviolet. Look here, this is the extreme red. Above it, you have infrared till 10 power 3 micrometer. Okay, يعني all the radiations that lie within the range 0.8 micrometer or 10 to the power 3 micrometer are infrared radiations. Okay? Let's take an exercise. Calculate the range the range of frequencies of white light. So to calculate, I have the range of lambda. So to calculate the range of the frequencies, I should use the formula that relate the frequency and lambda. So you have frequency equal C over lambda. Okay? Look here, the minimum value of ultraviolet, which is the extreme violet, lambda minimum is equal 0.4 micrometer. Change it to meter. This means 0.4 times 10 power minus 6 meter, which gives 4 times 10 power minus 7 meter. Keep in mind that 1 micrometer is equal 10 minus 6 meter. Okay? So now, if lambda is minimum, then the frequency here is maximum because they are inversely proportional. So frequency maximum is equal C over lambda minimum, which gives you 3 times 10 power 8 over 4 times 10 power minus 7, which gives 3 over 4, 0.75. Take this to the numerator, you get power 15 hertz, or 7.5 times 10 power 14 hertz. Okay? Now the maximum lambda is that of the extreme red. Lambda maximum is equal 0.8 micrometer, which is equal 0.8 times 10 power minus 6, which is equal 8 times 10 power minus 7 meter. Now lambda is maximum, so you get the frequency to be minimum. So frequency minimum is equal C over lambda maximum, which is equal 3 times 10 power 8 over 8 times 10 power minus 7, which is equal 3.75 times 10 power 14 hertz. Okay? Thus, the range of the frequencies is between the minimum value, which is 3.75 times 10 power 14 hertz, and 7.5 times 10 power 14 hertz. Notice here, the extreme violet has minimum lambda 0.4 micrometer, but maximum frequency. So this is the extreme violet. Okay? Also here, the extreme red has maximum wavelengths but minimum frequency. Yani the naming has reversed. Okay. I have one question here. سؤال. Ultraviolet معناتها الأشعة فوق البنفسجية. الانفراريد معناتها الأشعة تحت الحمراء. إذا بتطلع هون، طيب كيف الترافايولت الأشعة فوق البنفسجية وكيف جاية تحت الفايولت؟ حسب اسمها الترافايولت لازم تكون فوق الفايولت، هون جاية تحت الفايولت. كمان نفس الحكي الانفراريد معناتها تحت الحمراء. طيب حسب هيدي التسمية جاية فوق الحمراء. اوكي، يعني حسب هيدي التسميات، حسب اللمدة لازم تكون هيدي تحت البنفسجي وهيدي فوق الأحمر. اوكي، برأيكم ليش مسمينهم هيك؟ اوكي، هيدا السؤال، ليش برأيكم مسمينهم هيك؟ طيب أنا بقول لكم ليش. التسمية هون the naming doesn't come from lambda, it comes from the frequency. يعني الفريكونسي هير الاكستريم فايوليت هالقد، اللي فوق منه لانه انعكسوا صارت هيدي من هون ورايح صار الترا فايوليت، هون انفراريد، فاذا هون صار انفراريد. فاذا تسميه انفراريد والترا فايوليت هي حسب الفريكونسي مش حسب اللمدة. طيب شو السبب حسب الفريكونسي مش حسب اللمدة؟ السبب هو the reason is that the frequency is constant. It is independent of the medium. Okay, whereas lambda depends on the medium. دايما لما بدهم يسموا شيء ثابت بدهم يتكلوا على شيء كونستانت. اوكي، هيدي معلومه حلوه يعني. فاذا الفريكونسي doesn't depend on the medium, doesn't depend on the medium. عشان هيك بنستعملها للنيمينج، منا شيء ثابت. اوكي، فصار عندي هون الفريكونسي، هيدا الرينج اوف فريكونسيز whether light passes in vacuum or in glass or in water or in quartz. The range of lambda, this range of lambda of wavelengths will be fixed. But the range of lambda will change according to the medium. It is not fixed. This range between 0.4 micrometer or 0.8 micrometer is only in vacuum. Because of this, whenever write this range, you should write with it the medium in vacuum, which you don't need to do for the frequencies. Okay? Another information that you should know is that the color of light depends on the frequency. فإذا الcolor depends on the frequency and not on wavelength. Okay, who can give an interpretation? I will give you this. إذا ببعت لون أحمر من الهواء على المي بضله أحمر ما بيتغير. لو الكالر بيعتمد على الويف لينكس، كنت إذا ببعت ضوء أحمر من الهواء على المي الويف لينكس بدها تتغير، يعني الكالر لازم يتغير. فإذا هيدا دليل أنه الكالر depends on the frequency. فإذا the frequency determines the color. Now I am going to talk about the last part in electromagnetic waves, are the index of refraction. The index of refraction the index of refraction of a medium. Let's see. This figure also talks about the dispersion of light. This phenomenon is called dispersion of light when the white light is divided into its components. This is an animated figure. Okay, we talked about this before. Now, the index of refraction of a medium for a monochromatic light. Look at this figure. I have a monochromatic light, يعني light with one lambda, only one lambda, passing from vacuum to a medium. So, when it passes from vacuum to a medium, it will refract. Its direction of propagation will change and makes refraction. This is the incident ray, this is the angle of incident, this is the refracted ray and angle of refraction. And you studied this in first secondary. Now, when the ray is in vacuum, when the monochromatic light is in vacuum, its speed is c. Its wavelength is lambda, and its frequency is nu. When it passes to another medium, refractive medium, its speed will change, as we said, because the speed depends on the medium. Also, its wavelength changes. It is here lambda, it becomes lambda prime. Okay, lambda depends on the medium. And finally, the frequency remains constant. Okay, by definition, the index of refraction of a medium is equal to the speed of light in vacuum to the speed of light in the medium. Since C is in meter per second, will V in meter per second, you get an unitless. Okay? Now, C is greater than V. Large number over a smaller number, you get a result greater than 1. So always the index of refraction is greater than 1. And for air, V is approximately C. يعني this implies N للair is approximately 1. But the N of air is greater than 1. This means the N of air cannot be 0.99 مثلا. In reality, the N of a dry air is around 1.005, okay, which is greater than 1. Now, what is the relation between lambda C and the frequency? In vacuum. So in vacuum, lambda equals C over nu. Yani this implies C is equal lambda times nu. In a medium, the relation, similar relation, lambda prime is equal V over nu. This implies V equal lambda prime times nu. Substitute here in the definition of the index of refraction, you get N equal lambda nu over lambda prime nu. So nu cancel with the nu, and you get lambda over lambda prime. This formula should be proved when used. Okay, you prove it in this way, starting from here to reach this one. Now notice here, lambda prime equal lambda over N. Will N greater than 1, dividing number over number greater than 1, you get a result lambda prime less than lambda. Okay, and this is seen from here. Since lambda is proportional to the speed, and the speed of monochromatic light decreases when light passes from vacuum to a medium, then lambda decreases because lambda proportional to the speed, since the frequency is constant or period is constant. Last thing I want to say, that for every lambda and for same medium, the index of refraction varies. Okay? يعني الindex of refraction depends on the medium. Not here. Sorry, the index of refraction depends on lambda for the same medium. يعني not here. الآن depends on lambda for same medium. Okay? يعني for two different lambdas and same medium, you get different n, or you get different index n, which means, let's take an example. مثلا for a glass, if you have a monochromatic light of lambda equals 0.66 micrometer that passes from vacuum to glass, the index of refraction, red, for lambda equals 0.0 is equal to 1.662. For lambda violet, which is 0.4 micrometer, N will be, for this monochromatic radiation of lambda 0.4 micrometer, will be 1.698. So as you see, when lambda has changed, and for the same medium, which is glass, you get two different indices of glass. Okay? This is the end of this part of the chapter. يعطيكم العافية.